Swayam Prabha. Digital India. Educated India.
So students, now we have gradually come to the very last lecture on the shear strength of soils. We have seen 6 different aspects connected with shear strength of soils over the last 6 lectures, and today's is the concluding lecture on whatever items are still remaining with respect to shear strength of soils, which a typical students should know. As usual, let us take a quick look at whatever we had passed through in the last lecture. In the last lecture, we saw quite in detail what are the drained tests, what are undrained tests, both direct shear and triaxial shear, and where they are used, and we even saw some numerical examples. We also saw that it is possible to look at the topic of shear strength in a totally different way in terms of the soil. That is, how does cohesionless soil behave under shear and how cohesive soil behaves under shear. We saw in particular the application of the different types of drained and undrained tests with a typical example of the earth dam. During the course of the life of an earth dam, there are several stages it passes through, starting from construction to reservoir filling and drawdown to long term stability. And under each condition, the shear parameters which apply, which must be used in order to test the safety of the earth dam, will vary, and the type of test that will give the appropriate parameters will also vary. For example, the CD test was good, we saw, for a slow construction and also for long term stability, wherein consolidation would have already taken place, that means drainage would have occurred. Shear stress also does not produce any pore pressure. On the other hand, suppose a dam has already been filled, the reservoir is full, and the reservoir is emptied somewhat suddenly, rapidly, relatively, for certain purpose. Then the test that is applicable and the corresponding parameters would be the consolidated undrained test, because the earth dam has already undergone the consolidation during its lifetime, during filling up of reservoir. But now sudden depletion of the reservoir produces shear stresses under undrained condition. And if suppose we are building a dam very rapidly, then pore pressures get developed even during construction, they do not have time to dissipate, and therefore the stability of a dam even during construction has to be kept in mind, and that short term stability is best determined under undrained conditions using parameters derived from a UU test. So, if you take construction, if it is slow and pore pressures are allowed to dissipate, there is consolidation and drainage. S is equal to C dash plus sigma dash tan phi dash, where all the parameters involved are drained parameters and effective parameters. If the construction is on the other hand rapid, pore pressures are not allowed to dissipate, the shear strength equation becomes S is equal to Cu plus sigma tan phi u, where Cu and phi u correspond to undrained conditions. If drawdown is being considered, the parameters which will be applicable will be CCU and phi CU, and the shear strength equation would be S is equal to CCU plus sigma tan phi CU. Under long term conditions, once again drained parameters will apply, and S is equal to C dash plus sigma dash tan phi dash. There are a number of factors which affect shear strength. We must know them and their influence, and so we spent quite some time in the last lecture to understand the impact of each one of the many factors which affect the shear strength. Here is simply a list which I am reproducing to remind what are the factors which influence shear strength. The first three factors, shape and gradation of particles, relative density, the compaction, the density with which, the denseness with which the soil is packed, and the confining pressure that is applied to the soil or the confining pressure under which the soil is at any given depth. These are all parameters which are particularly important from point of view of shear strength of cohesionless soils. On the other hand, for cohesive soils, what are more important, obviously because of their low permeability, are drainage conditions, degree of saturation, rate of loading. In addition to this, there is another important parameter which during the course of today's lecture we will pay some attention to, that is the stress history, the history which shows what kind of stress the soil has undergone in the past. This is particularly important for clayey soils. Here is a look at shear strength from point of view of the type of soil. So, if you have a cohesionless soil and subjected to direct shear test, this is the kind of relationship you will get between shear stress and the shear displacement. If it is a dense soil, it will undergo a little bit of compression and then expansion. If it is a loose sand, it will undergo compression continuously. There will be a peak shear stress and an ultimate shear stress as the displacement increases. The same thing can be observed in a traxial test also. For a dense sand there is a peak, for a loose sand there is no marked peak. A loose sand undergoes compaction or compression, dense sand undergoes a little bit of compression initially, but then undergoes expansion subsequently. It becomes loosened. So, with respect to behavior of a soil, whether it is cohesional or cohesive, under shear we can see a few special points which are summarized here. One, there is a peak and an ultimate, which we saw in the previous diagram. Dense sands undergo an expansion mostly, although they undergo a little bit of compression initially. Loose sands undergo compression. There is a significant volume change. The amount of compression or the amount of expansion is quite significant under shear. Now, suppose we prevent this volume change, then what will happen is the shear stress that is responsible for causing this volume change will not be borne by the soil, and the soil will tend to behave like a liquid, and that is known as liquefaction. We also saw last time, having talked about liquefaction, what is critical void ratio and how that can be used to decide whether a soil will liquefy under a given condition or not. The concept of critical void ratio can be very easily understood from the statement which I made a few minutes back, that dense sands undergo expansion, loose sands undergo compression. But suppose you have a sand which is neither loose nor dense relatively speaking, then if the void ratio remains unchanged throughout shear, then that is the soil which will undergo liquefaction, because it does not undergo volume change during shear, and since it is unable to undergo volume change during shear, it will liquefy. So, what is that void ratio at which the soil will behave like this? That can be obtained by plotting void ratio change with axial strain as shown here, and finding out which is the void ratio where the volume change will be nullified, and that is known as CVR. Depending upon the type of traxial test we do, there are different values of CVR. The most popularly used one is the Casagrande CVR. which is nothing but the void ratio before application of sigma 3, and constant sigma 3 CVR also is possible, constant volume CVR is also possible to determine. And in the second instant, where the constant volume CVR test is conducted, E0 after the application of sigma 3 is used as the critical void ratio. Now, in today's lecture, we will see an assortment of topics which I am calling as special topics, all of which are very important. Some of them are slightly advanced, and I will try to give an exposure to these topics rather than go into great details. For example, let me start with a list of these so called special topics. Peak and residual shear strength is something which we need to understand very well, which is very important from point of view of particularly slope stability or stability of any structure either also. Then we need to understand something known as pore pressure coefficient. Then what are stress paths? I had mentioned that the shear strength of a clay soil particularly depends upon the stress history. So, one needs to know what is the path through which the stresses have changed. Then we need to know something about failure. We have only been seeing so far the Moore-Coulomb theory, but there are other theories as well, because sometimes the soils do not behave strictly according to the Moore-Coulomb theory, although it is universally valid and universally used also. But there are theories which are particularly applicable to clays, especially in the plastic deformation stage, and those are known better as yield theories. We will have to see those also. And then finally, we will see a very important test called cyclic triaxial test. These are days where awareness about earthquakes and their damage has increased like anything because of past recent experiences. There is one test known as the cyclic triaxial test, which is useful in determining the liquefaction strength of a soil. It helps us to predict under what conditions a soil will liquefy and whether the present condition is indicative of a potential to liquefy or not. So, site characterization, site assessment from point of view of liquefaction can be carried out using this cyclic triaxial test, and it indirectly obviates the need for using the concept of CVR. The concept of CVR is now gradually being replaced by another concept based on the cyclic triaxial test. Let us start with peak and residual shear strength and their utility. If you take a normally consolidated soil, you will have a shear strength versus displacement curve, which will be something like this, which shows a peak, and then it comes down and shows a residual value. With large displacements, the value goes beyond the peak and then comes down and remains almost constant. So is the case with over consolidated clays also. There is a peak and then a residual value, but what is obvious from these two figures is that when the soil is over consolidated, the fall to residual is much more. After reaching the peak, the drop in shear strength is much more with displacement in over consolidated clays. Now, if I were to plot the Moore envelopes for the normally consolidated clay and the over consolidated clay for peak shear strength as well as for residual shear strength, then for the normally consolidated clay under drained conditions, the peak shear strength envelope will be depicted by, let us say, this yellow line. Then the residual friction angle will be obviously slightly lesser, and that will fall somewhere below like this. Whereas if we have an over consolidated clay, the peak will be much more than in the normally consolidated soil, and it will even show a small amount of cohesion intercept. And as I mentioned, the drop from peak to residual in the case of over consolidated soil is much more than in the case of normally consolidated soil, and therefore the over consolidated residual strength envelope will invariably be below the normally consolidated residual strength envelope. The sequence in which the envelope keeps coming down is practically constant and valid for all clays. The over consolidated peak strength is very high, over consolidated residual strength is very low. The normally consolidated strengths lie between these two. So, some of the points that arise from this discussion are: there is a more pronounced reduction in over consolidated clays from peak to residual. And another point that is worth mentioning is, higher the clay content, greater is the reduction from peak to residual. The drop in strength with displacement is more if the clay content is more in the soil. The residual strength incidentally is independent of the stress history. It is only proportional to the effective stress that is applied, and you can see that in fact that the residual strength remains almost practically constant with displacement, and irrespective of what stress history the soil has experienced, it will eventually have a certain residual strength beyond a certain level of displacement. Generally, the residual strength envelope is lower than the peak strength envelope for over consolidated, and therefore also the normally consolidated clays. Now, we will pass on to the next special topic, the pore pressure coefficient. One of the important things in a triaxial test is measurement of pore pressure during the application of the confining pressure as well as the deviatoric stress. In fact, we have seen in such great length in our previous lectures how the pore pressure varies during the conduct of the test for consolidated drained, consolidated undrained and unconsolidated undrained tests. We had mapped very systematically as how the confining pressure is applied and the deviatoric stress is applied, how the pore pressure changes, and therefore how the total stress and the effective stresses change. And what is important therefore is to know how the pore pressure changes during the course of a test as the stresses are applied. In other words, one other way to say is it possible for us to know what the pore pressure change is likely to be, not necessarily only by conducting a test, but by using a simple relationship, fundamental relationship. Skempton in 1954 derived a very fundamental relationship from basic considerations for evaluating the change in pore pressure during a triaxial test due to the application of the confining stress sigma 3 and then the deviatoric stress. The relationship is extremely simple. Delta U, the change in pore pressure, is simply a function of delta sigma 1 and delta sigma 3 which are applied. So, here it is, there is a triaxial specimen, we first apply sigma 3 and then we apply the deviatoric stress. The change in pore pressure, net change that will be produced will obviously be proportional first to the incremental stress in the lateral pressure, lateral direction, that is delta sigma 3, and an increment, component of increment due to the deviatoric stress. This obvious relationship between the change in pore pressure and the applied stresses. Now, the constants B and A are what are known as Skempton's pore pressure parameters, and those are the parameters which are very important to know, and if you know those parameters for a given clay, then it is possible to make a reasonably good guess about the change in pore pressure due to change in stresses. This is a very important convenience when it comes to solving or addressing practical problems, where given a stress change, you will be able to predict what will be the change in pore pressure that is likely to occur. Let us take a look at what these parameters are, or what are their likely values. Obviously, parameter B has to be, since it depends upon delta sigma 3, it is equal to 1 for a fully saturated soil. In a fully saturated soil, the moment you apply delta sigma 3, an equivalent amount of pore pressure will be generated, and therefore B has to be equal to 1 for a fully saturated soil ideally. And then in general, as saturation improves, B will go on increasing until under full saturation it becomes 1. Under partly saturated conditions, B will be less than 1. As for the parameter A, the parameter which is of interest is really the value at failure, because on the application of the deviatoric stress sigma 1 minus sigma 3 and bringing the sample to failure, what is the maximum amount of pore pressure that would have got generated and what is the corresponding coefficient AF at failure. That is what is of interest. For normally consolidated clays, this AF is approximately equal to 1, that is whatever deviatoric stress you apply also gets converted into the pore pressure. But if it is an over consolidated soil, AF is a function of OCR, and for heavily over consolidated clays it could even be negative. Typical value is minus 0.2 or minus 0.3 and so on. Let us take a simple example of the use of the pore pressure parameter. Let me read out the example. A triaxial test specimen from a saturated clay sample is subjected to a cell pressure of 60 kilonewton per meter square. That means a clay sample is taken and a specimen is extracted from that, and it is subjected to a cell pressure of 60 kilonewton per meter square in a triaxial experiment. And the initial suction pressure in the specimen is 35 kilonewton per meter square before it is saturated, and then after saturation and conducting the triaxial test, particularly a consolidated undrained test in this case, C dash is found to be 0, phi dash is found to be 20 degrees, and the parameter AF at failure is found to be minus 0.2. What is of interest here is what was the suction pressure that was originally present in the soil before it was saturated and tested in the consolidated undrained test. It is very easy to compute this. Now, we know that pore pressure at failure UF is the initial pore pressure U0, whatever was there in the sample, which is what is not known. U0 is what is not known, and that is what is required to be determined. The pore pressure at failure will be UF is equal to U0 plus delta UF, or whatever change in pore pressure is taking place during the test. Now, we know that the change in pore pressure that takes place during the test can be expressed in terms of the pore pressure coefficients. So, using Skempton's equation, delta UF will be equal to the parameter B into delta sigma 3, which is applied, plus the parameter AF into the deviatoric stress A1 sigma 1 minus sigma 3. Now, this being a saturated sample, when the test is actually started, the sample is saturated, and therefore, B can be taken as equal to 1, and AF is given to be minus 0.2, and the initial suction pressure is minus 35 and the final pore pressure is 70. Let us take a look at the problem again before we go further. So, now we know that UF has to be equal to this initial pore pressure minus 35 plus 70 minus 0.2 into the deviatoric stress dF, or 70 minus the final pore pressure is 35 plus 0.2 dF. Now, you may recall that from simple considerations of Moore's circle, we can derive a relationship shown here, C cot phi plus sigma 3 by C cot phi plus sigma 3 plus deviatoric stress equal to 1 minus sin phi by 1 plus sin phi. This is very useful for us in determining the final pore pressure. If I apply this above equation, I know C dash is 0, phi dash is 20, sigma 3 dash we have just seen is 70 minus the final pore pressure. So, if I substitute that here, I will have C being 0, C cot phi becomes 0, and sigma 3 is nothing but in terms of effective stress 70 minus UF, and the denominator will become 70 minus UF plus the deviatoric stress D, capital DF, and this must be equal to 1 minus sin phi by 1 plus sin phi, and phi is 20 degrees, which gives us that the right hand side is equal to 0.49. Now, from this we find that DF is 45.77 kilonewton per meter square, and the shear strength, undrained shear strength which we were interested in is 22.9 kilonewton per meter square. So, this illustrated the use of the pore pressure parameter in determining the final pore pressure and hence the strength of the soil. Now we pass on to another important topic known as stress paths. What is a stress path? Let us take a look at the basic definition. It is the locus of all points, that is, it's a line joining a certain points which depict a specific stress state as loading gradually progresses through various stages and causes finally failure. So, suppose we are testing a sample in say traxial test, it is subjected to loading at different stages, different amounts of loading at different stages. The stage through which the loading goes and leads to failure is what is known as the stress path. Let us take an example. Here is an example of a stress path which is showing how the maximum shear stress is varying as loading changes in a typical traxial test. Here is the sigma tau plot and here is the corresponding PQ plot. From the sigma plot, we know very well that if 3 tests are conducted, the traxial test, 3 successive Morse circles can be obtained, and if I take the stress state corresponding to the maximum shear stress, that will obviously be the point at the top of the semicircle here. Then as the loading has changed during the test with every Morse circle, the position of maximum shear stress point has changed from here to here to here. And in a PQ graph, we can see the same path through which maximum shear stress has changed with loading. It is this what is known as the stress path. This stress path is for maximum shear stress and how it varies with loading. Now, here no failure is involved at the moment. Now, suppose I continue the test and a few more tests are conducted, a few more specimens are tested, and ultimately we reach a set of sigma 3 sigma 1 combination which makes the soil fail. That means the last Morse circle shown here is touching the failure envelope. Same thing is true here in the PQ graph. Now, if I take the points corresponding to maximum shear stress from each one of these Morse circles and plot, you will find the progression of the maximum shear stress during the test from a low value here gradually to a point which sits on the failure envelope, indicating that is the point of failure. So, this is an example of stress path for maximum shear stress up to failure. Now, if one knows this stress path, one knows what kind of stress history the soil has gone through and what has led to failure, and that is very important because that throws insight into the behavior of a soil subjected to loading and how it gradually tends to move towards a state of failure. Here is another example of stress paths. Suppose we do a lot of tests continuously, one after the other, on a same specimen, but with constant sigma 3 and only sigma 1 goes on changing. And again, let us take the maximum shear stress point, those will be at constant sigma 3, A, B, C, D, E. And if you now plot them on the PQ graph, you get a straight line at 45 degrees. And this is nothing but a maximum shear stress path corresponding to sigma 3 constant state. Now, here is another diagram, a PQ plot, which shows us different stress paths, other different forms of stress paths under different other conditions. We just saw that at sigma 3 equal to constant, we have a stress path which is at 45 degrees. If on the other hand sigma 1 is kept constant, the stress path would have been as shown here on the left of this diagram. And if on the other hand we had kept sigma 1 plus sigma 3 by 2 as constant and conducted the test and plotted the points of maximum shear stress, then we would have found that those would have led to a stress path which is going straight upward. Let me now give you a very interesting illustration of the application of this stress path and how it has led to a better understanding of the effect of rainfall on slope and subsequent failure and landslides. So, an interesting illustration of the significance of stress path can be quoted as the effect of rainfall. When rain occurs on a slope, infiltration is caused. The rainwater gradually flows into the earth. Soil is initially partly saturated, and therefore, as infiltration takes place, gradually the suction pressure which is there in the partly saturated soil is neutralized. Positive pore pressures gradually start developing, and because of this, the initial tension which was binding the particles in the partly saturated condition, capillary tension which was holding the particles together during partly saturated state, now gradually gets nullified, and the effective stress therefore gets gradually reduced. And you know what will happen if the effective stress goes on getting reduced, the shear resistance goes on decreasing, and therefore ultimately a stage is reached where the effective stress reduces to such an extent that the slope fails finally. But during all this process, we must remember that the total stress in the system remains unchanged. Neither an external stress is applied nor an internal stress is disturbed, just the pore pressure goes on changing with total pressure remaining the same. This is a very interesting concept that has been developed by Brand to explain the phenomenon of rainfall induced landslides. So, this implies that total stress remaining same, the slope is gradually coming to failure because of increase in pore pressure. That means the stress path has to be horizontal, that we will see in the next slide. The conventional laboratory test unfortunately does not help you to simulate this horizontal stress path, and therefore, we will have to devise a special testing technique. Cyclic triaxial test could probably be an alternative. In the next slide, we will see how the stress path really varies, what kind of stress path we get in our conventional tests, and what should be the real stress path that should be simulated. Here we have the stress path which actually exists during rainfall. This arrow going from right to left shows how the initial values of P dash and Q dash gradually change to the final failure state P dash Q dash with total stress remaining same. So, this is the true stress path in the field. The soil undergoes change in stress according to this path. Now, suppose this is the failure envelope. The soil reaches failure, or the slope in question reaches failure through this horizontal stress path with total stress remaining same, and it touches the failure envelope finally. If on the other hand you do a consolidated undrained test or a consolidated drain test, because the slope has been in existence for some time, consolidation has taken place, and now suddenly a rainfall occurs and the slope fails. So, consolidated drained or consolidated undrained are the appropriate tests depending upon the rate of infiltration of water or the rate of rainfall. Usually the rainstorms are so heavy, consolidated undrained conditions are more preferred as the representative ones rather than the consolidated drained. So, if you see here, the stress path for consolidated drained test is given by this green line, and that goes and meets the failure envelope like this. This is the path that will be followed, whereas if it is consolidated undrained, this is the path that will be followed to failure, and none of these paths unfortunately depict what is really taking place in the field, and therefore, we need to know and have a method by which we can simulate this if we really want to determine the correct shear strength parameters for a slope which has failed due to rainfall. Now, we pass on to an important topic from point of view of failure of soil, since we are now talking about failure: octahedral stress failure theories. What are octahedral stresses and what are failure theories associated with that? Here is a very simple illustration of three-dimensional stress state: sigma 1, sigma 2, sigma 3. This is a stress cube which shows what are the stresses on different planes. We are interested in one particular plane depicted here as ABC. What is special about this plane is that this is a plane on which sigma 1, sigma 2 and sigma 3 are equal. If you take a perpendicular to this plane, that is a line showing hydrostatic stress state. The perpendicular to this plane will have sigma 1 equal to sigma 2 equal to sigma 3 along it, and such a plane is a very special plane known as the octahedral plane, and the octahedral normal stress and shear stress on this particular plane are given by these two equations. And what is special about this again is, this is total stress in terms of octahedral stresses, and if you consider pore pressure, then pore pressure will get subtracted from each one of these stresses, and therefore effective sigma octahedral would simply be this minus u, whereas effective shear stress octahedral will not change, it will be the same as the total octahedral shear stress. The octahedral stress state is a very important stress state to know, because this plane ABC is often very close to the actual failure plane observed in the soil under different stress states, and many of the failure theories make use of the octahedral stress which is known and which can be determined, and from that they derive their yield theories and predict whether or not a soil will yield. We take a look now at one important failure theory other than the Mohr-Coulomb theory. This is known as the Drucker-Prager theory, and it is quite applicable to soils. We know that in the Mohr strength theory, the failure envelope is a straight line in two-dimensional stress state. In three-dimensional stress state, it is not a straight line. If you look at this figure, for example, this is a three-dimensional stress state figure, sigma 1, sigma 2, sigma 3 are shown axis, and now suppose you plot all those points which correspond to failure as predicted by the Mohr-Coulomb theory, then what you will get will be in 3 dimensions a hexagon like this, a hexagonal hollow surface. That is what you will get. In 2 dimensions it looks as a straight line. What Drucker-Prager theory says is that Mohr-Coulomb theory does not predict failure appropriately in certain conditions, and they have modified the Mohr-Coulomb theory particularly to account for behaviors such as strain hardening with displacement, and they have given a slightly modified equation for predicting the strength or yield. Here is one equation and here is another. They are actually similar, they are merely 2 different forms of writing the same failure condition as per the Drucker-Prager theory. Both Mohr-Coulomb surface and the Drucker-Prager surface are shown in this figure. The hexagonal surface corresponds to Mohr-Coulomb yield theory, whereas the conical surface refers to Drucker-Prager yield theory. In cross section, it will look like this, the hexagon and the Drucker-Prager circle. Now, do these theories match at all? How deviant are they from each other? The Drucker-Prager theory can be fitted to the hexagon of the Mohr-Coulomb theory either by fitting a circle which circumscribes the hexagon or by inscribing a circle within the hexagon. Accordingly, we will have some equivalence between the Mohr-Coulomb theory and the Drucker-Prager theory. The equivalences of course will vary depending upon whether we are using outer circle or the inner circle. In these 2 equations which are given here, K is a material parameter, alpha is a material parameter, so is beta, and J2, MS, these are all matrices involving the mean stress or the stress invariants. I shall not go into very great detail about what is stress invariant, what are the mean stresses. Suffice it to know that there is a theory known as the Drucker-Prager theory, and it is quite widely applied in order to predict yield in soils, particularly clayey soils. Now, if I use the circumscribed circle over the outer apices of the Mohr-Coulomb hexagon, then the values of alpha and k that will need to be determined and used in the Drucker-Prager theory will be given by these formulae. Obviously, if we know the friction angle for the soil, you can determine the parameters that will go into the Drucker-Prager theory, alpha and k. The parameters that will go into the Drucker-Prager theory depend upon the conditions under which the soil is subjected to various different types of stresses. Suppose the soil is subjected to 3-dimensional stress state, alpha will be given by 2 sin phi by root of 3 into 3 minus sin phi, and k by another similar equation. If plane strain conditions prevail, then this tan phi by 9 plus 12 tan square phi to the power of half is the corresponding applicable value of alpha. And if on the other hand we use the inscribed circle which is within the hexagon, then alpha and k will become values shown in the last two columns of the table here. Depending upon whether we are analyzing a plane strain problem or whether we want an upper bound or a lower bound, we can choose the appropriate values of alpha and k in a typical analysis of say a tunnel or a slope using a finite element technique, for example. There are other models as well, although it is beyond the scope of this lecture to go into great details about these other models. One model is of special interest and it is worth making a mention about it, although not much in detail. This is known as the critical state model. There are two different models proposed under this. One is known as the Cam-Clay model, another is known as the modified Cam-Clay model. These were proposed by Andrew Schofield in Cambridge. The basic considerations in development of these models were what is the strength of the soil, the change in volume that takes place during shear, then what are those critical states corresponding to large deformations without stress change or volume change. If you think of liquefaction, it is very easy to comprehend the meaning of this statement. Liquefaction is nothing but a case of large deformation at constant stress or constant volume, and therefore, the Cam-Clay model attempts to explain these large deformations which may take place under constant stress or constant volume conditions. The state of the soil is characterized by 3 parameters. As in the Drucker-Prager theory we had 2 parameters, here we have 3 parameters. The Mohr-Coulomb theory has again only 2 parameters, C and phi. The Cam-Clay model on the other hand uses P dash and of course Q dash, but it also uses the specific volume V. Here are the yield curves which will result if we use the Cam-Clay model. Here is the yield surface on the PQ plot for Cam-Clay. This is for the modified Cam-Clay, and this is the line which tells us which are those critical stress states at which a soil will, either according to the Cam-Clay model or according to the modified Cam-Clay model, correspond to a situation where there is a yield or where there is a large deformation. So, this point or this point will represent the point, either this or this will represent a situation of large unlimited deformation as in the case of liquefaction, and this can be predicted reasonably well using the Cam-Clay or the modified Cam-Clay model. Now, lastly we come to the test called cyclic triaxial test, about which I mentioned some time back, which is a very useful triaxial test and is a very innovative, relatively recent development and completely digital usually, and is of interest to know. Here is a simple illustration of a cyclic triaxial equipment. This has the facility to apply cyclic loading, and that is why it is called cyclic triaxial test. It is a conventional triaxial test, except that the load that can be applied can be cycled. Suppose you take earthquake as an example. Then the load due to an earthquake can be considered to be somewhat cyclic in nature. It is repetitive, and therefore, if we want to really understand the effect of earthquakes on shear strength of soil, we must conduct the triaxial test under conditions of cycled loading. Cyclic loading must be possible. So, this equipment permits precisely that. You can apply load in terms of forces and have control over the force applied. You can apply the load indirectly by inducing a strain. A direct shear example for is a test where we induce strain and produce the shear forces appropriately. So, this could be strain controlled, it could be force controlled, it could be displacement controlled also. And different types of loadings are permissible because this is usually digitally computer controlled. The different types of loadings that can be applied can also be such as to simulate a given earthquake. A given earthquake loading, if you simulate and conduct the test under those conditions, the parameters which you get from this triaxial test will be the best that one can get in order to truly analyze the behavior of a soil under earthquake conditions. It permits, the equipment has the facility to saturate the sample, to consolidate the sample, and to apply cyclic loading, and then finally to shear the sample. That is what the cyclic triaxial testing system is capable of doing. Now, this can be used to understand and predict liquefaction in a very ingenious way. This is a typical scenario that was found during the Bhuj earthquake on 26 January 2001. This shows large scale flow of soil, and this is exactly what is known as liquefaction. And this is the earthquake spectrum which produced this kind of a liquefaction. So, suppose you know the spectrum, suppose you want to identify the potential for liquefaction in a given soil, then the cyclic triaxial test is a wonderful test for this purpose. Here is a typical plot that may be applied from a typical cyclic triaxial test. You apply a number of cycles and find out when the liquefaction starts. Then plot the number of cycles which causes initial liquefaction against a ratio known as the cyclic stress ratio, sigma d by 2 sigma 0 dash. Let us see in the next slide what this represents. Initial liquefaction is the state in which pore pressure builds up to a value equal to the initial confining pressure. That means it completely neutralizes the initial confining pressure, and therefore the soil starts liquefying, or where strains reach very high values, for example 5%. Now, if you do a cyclic triaxial test and identify the number of cycles at which one of these conditions is satisfied and liquefaction takes place, and then plot the cyclic stress ratio against it, you get a relationship from which you will know whether or not liquefaction can take place. The cyclic stress ratio for simple shear test is given by this parameter. For triaxial shear test, it is given by sigma d by 2 sigma 0 dash, where each one of these symbols represent different shear and vertical stresses under different amplitude conditions as listed here. Suppose you want to relate the simple shear test results with triaxial shear test results. That is possible by relating the cyclic stress ratios through a parameter alpha c, and incidentally this alpha c depends upon octahedral dynamic shear stress divided by effective static octahedral normal stress. So, this shows how in yield theories the octahedral shear stress plays an important role. Now, we come to the end of the chapter of shear strength of soils, and here are a few questions which you are well advised to try to answer. Suppose you go back through this lecture, then you will find an answer to a question: is undrained test valid for sand, and if so, when? What is liquefaction and when does it occur, and y. A slope has been in existence, let us say, for quite some time. Now, what kind of test will you do in order to get the strength parameters which are required to analyze its present state of health? Try to answer these questions. The answers have been given by me during the course of my lecture. They are available in the slides which had been displayed some time back. Try to also solve a simple problem. For example, here the unconfined compressive strength of a saturated clay is given, and when it is subjected to a triaxial shear test, the pore pressure coefficient AF is found to be minus 0.2. C dash and phi dash determined from the test are 5 and 20. Now, try to find out the undrained shear strength. Now, incidentally, in this particular case, although the values of C dash, phi dash are given, AF is given, it is very obvious right from the statement of the question that it is the compressive strength 120 divided by 2 which gives you the shear strength, and therefore, the undrained shear strength is readily available here as half of the compressive strength, 60 kilonewton per meter square. You can understand this better if you go back to my illustration and explanation of the unconsolidated undrained test. Now, the other data that is given in this particular problem is useful for determining the initial pore pressure, and you can determine this in a manner similar to the recent problem which we saw in this lecture, that is the problem number 17. Using the similar expression, you can find out that the initial pore pressure is 77.55 kilonewton per meter square in this particular case. Now, suppose you have two different veins and you test the same soil for strength with these two different veins. How do we get the shear strength of the soil in the horizontal and the vertical planes? This can be done by going back to fundamental equations of torque generated in a vein shear test. By using the individual equations for torque for each vein and the ratio of the torques, and by knowing the geometry of the veins, one can easily determine SUH and SUV, which are the required shear strengths in the horizontal and the vertical directions. We have used a number of terminology. You are advised to go through this complete list of terminology and understand their real meaning and significance in practice. The terminology are strain and stress control tests, constant sigma 3 test, CD, CU and UU tests, critical void ratio and liquefaction, peak and residual strengths, stress paths, cyclic stress ratio, octahedral stresses and yield theories. Here is a list of books which will be useful to you for going through and understanding in greater detail whatever I have attempted to cover in these lectures. Here are a few more references. With this we come to the end. Thank you.